Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will see the effect of the negative feedback on the amplifier in detail. So in the previous video, we have seen the general structure of the feedback amplifier and we have derived the expression of the closed loop gain of the amplifier. So we have seen that if the A beta or the loop gain of the feedback amplifier is very large, then this closed loop gain is approximately equal to 1 divided by beta. And in that case, the gain of the feedback amplifier can be decided just by using the feedback network. And briefly, we have also discussed the benefits of the negative feedback on the amplifier circuit. So in this video, through a mathematical analysis, we will understand all these effects in detail. So in the previous video, we have already seen that due to the negative feedback, how the gain of the amplifier reduces. Because with the negative feedback, the closed loop gain of the amplifier is equal to A divided by 1 plus A beta. That means due to the feedback, this gain of the amplifier reduces by the factor of 1 plus A beta. But at the same time, we are also getting other benefits. So one by one, let us see each one of them in detail. So this negative feedback desensitizes the gain of the amplifier. That means due to the temperature or some other external parameters, even if there is a variation in the open loop gain of the amplifier, then also the variation in the closed loop gain will be minimal. So to understand that, once again, let us take the example of the op-amp. So as you can see, here the op-amp is configured in the non-inverting configuration. So here, we are taking the same values of the R1 and R2 which we have taken in the previous video. That means here, this R1 is equal to 1 kilo ohm while the R2 is equal to 9 kilo ohm. That means here, this feedback factor is equal to R1 divided by this R1 plus R2, or that is equal to 1 kilo ohm divided by 1 kilo ohm plus 9 kilo ohm, or that is equal to 0.1. And let's say initially, this open loop gain of the op-amp is equal to 10 to the power 6. So now, let's say, because of the external parameters, this open loop gain of the op-amp reduces by the 20%. So now, this open loop gain will become 0.8 times this 10 to the power 6. So with this open loop gain, if we see the closed loop gain of this non-inverting amplifier, then that is equal to A dash divided by 1 plus A dash times beta, where this A dash is equal to 0.8 times this 10 to the power 6. And if you see this A dash dot beta, then that is equal to this A dash times 0.1, and that is equal to 0.8 times this 10 to the power 5. So if you see the value of the closed loop gain, then that is equal to 9.9998. So as you can see, even if there is a 20% variation in the open loop gain, then also there is a hardly any variation in the closed loop gain. So we can say that this negative feedback desensitizes the gain of the amplifier. So now, let us go little bit into the deep, and through a mathematical analysis, let us understand even if there is a variation in the open loop gain, then by what factor this closed loop gain will get affected. Or in other words, what is the variation in the closed loop gain. So here, this closed loop gain of the feedback amplifier is equal to A divided by 1 plus A beta. So now, let us differentiate this expression with respect to A. So here, we are assuming that this feedback factor beta is constant. So if we differentiate with respect to A, then we can write it like this. That means in the denominator, we will have the 1 plus A beta square, while in the numerator, the first term will be equal to 1 plus A beta times 1. That means the denominator will remain as it is, and we will have the differentiation of the numerator. And then after, the numerator will remain as it is, and we will have the differentiation of the denominator. So that is why the second term is equal to minus A beta. So overall if we see, then that is equal to 1 divided by this 1 plus A beta whole square. So further we can write it as this DAF, that is equal to dA divided by this 1 plus A beta whole square. So now, let us divide this expression by this first expression. So now, we can write it as this DAF divided by AF, that is equal to this dA divided by 1 plus A beta whole square divided by this A divided by 1 plus A beta, or we can write it as is 1 plus A beta divided by A. So if we further rearrange it, then further we can write it as this dAF divided by AF, that is equal to is 1 divided by 1 plus A beta times dA divided by A. So as you can see, the variation in the closed loop gain, that is dAF divided by AF, is lesser than the closed loop gain by this factor, that is equal to 1 divided by 1 plus A beta. That means the negative feedback desensitizes the gain of the amplifier. And if the A beta or the loop gain is very large, then the gain remains almost constant even if there is a variation in the external parameters. So similarly, if we see the second positive effect of the negative feedback, then it reduces the nonlinear distortion in the amplifier. So many times, the amplifier does not provide the same gain for the all signal levels. So it is quite possible that the higher signal levels may see a different gain than the lower signal levels. So here for the simplicity, a piecewise linear characteristic is shown for the one amplifier. So as you can see, up to a certain voltage level, the gain provided by the amplifier is equal to 1000, and then after it provides the gain of the 100. So this is basically a transfer characteristic of the amplifier. And as you can see, since it is a not linear, so this nonlinear distortion may occur in the output of the amplifier. So now let us see what happens when the same amplifier is used with the proper feedback. So let's say when the same amplifier is used with the proper feedback, then the feedback factor is equal to 0.01. So now in this region, with the feedback, if we see the closed loop gain, then that is equal to this 1000 divided by 1 plus 10. Because for this region, this gain A is equal to 1000, while if we calculate the value of A beta, then that will be equal to 10. So if we see the closed loop gain, then that will be equal to 90.9. Similarly, for the second region, this open loop gain is equal to 100. So if we calculate the value of the closed loop gain, then that will be equal to this 100 divided by 1 plus 1. Because here, the value of the A beta is equal to 1. And therefore, this closed loop gain will be equal to 50. That means now, with the feedback, if we see the transfer characteristic of the amplifier, then it will look like this. So in one region, now the gain is around 90, while in the second region, the gain is equal to 50. So earlier without the feedback, if we move from the one region to the other region, then there was a tenfold decrease in the gain. But with the feedback, it has been reduced substantially. And now, the characteristic is almost linear. That means with the proper feedback, all the signal levels will see almost constant gain. So with this negative feedback, although it is possible to achieve this almost linear characteristic, but we need to pay the price in terms of the reduction in the overall gain of the amplifier. So if we want to achieve the same gain, then what we can do? We can add one preamplifier which provides the required additional gain for this amplifier circuit. For example, in this case, let's say this preamplifier provides the gain of the 10. So in this case, this preamplifier will not add the nonlinear distortion, because here, if you see the gain of this preamplifier, then it is very less. That means the signal levels even at the output of this preamplifier will be less. And because of that, it will not see the effect of the nonlinear distortion. And in the next stage, we can use this feedback amplifier. And in this way, it is possible to achieve the desired gain. So in short, using this negative feedback, it is possible to reduce the effect of the nonlinear distortion. So apart from that, this negative feedback also reduces the effect of the noise or the interference in the amplifier circuit. Or more precisely, it can increase the signal to noise ratio. So when the amplifier is configured in a certain way, then it is possible to achieve that. So let's say we have one noisy amplifier. So whenever some input signal Vs is applied to that, then along with that, this noise signal Vn also gets amplified. So for this amplifier, at the output, if we see the signal to noise ratio, then that is equal to this A times Vs divided by A times Vn, or we can say that is equal to Vs divided by Vn. So now let us assume that it is possible to build another amplifier which does not suffer from the noise or the interference. That means whenever the signal is applied to that amplifier, then it only amplifies the input signal and it does not amplify the noise signal. So what we can do? We can place this amplifier just before the noisy amplifier. And then after, we can apply the feedback around the cascaded stage in such a way that the overall gain of the amplifier circuit will still remain the same. So here, this A2 is the clean amplifier and this A1 is the noisy amplifier. And this A2 and A1 are the gain provided by the each amplifier. And here, this beta is the feedback factor of this feedback network. So now, if you see over here, then we have the two voltage sources, that is Vs and the Vn. So here, by applying the superposition theorem, we can find the overall output of this feedback amplifier. So first, let us assume that only this voltage source Vs is acting alone and this Vn is equal to 0. So let's say in this condition, this output voltage is equal to VO1. So in this condition, if you see the overall gain in the forward direction, then that is equal to A2 times A1. And here, this feedback is equal to beta. So in this condition, if we see the output voltage VO1, then that is equal to A2 times A1 divided by 1 plus this A1 times A2 times beta. And of course, it will get multiplied by this input signal. So similarly, now let us assume that this voltage source Vn is acting alone and this voltage source Vs is equal to 0. So in this condition, now this Vn is acting as the source signal. That means now the gain in the forward direction is equal to A1. While if we see the feedback path, then the overall feedback factor is equal to A2 times beta. And after this amplifier A2, the output voltage that is equal to A2 times beta times Vout will be subtracted from the noise signal. So we can say that over here, this feedback factor is equal to A2 times beta, while the forward gain is equal to A1. And in this condition, if we see the output voltage VO2, then that is equal to A1 divided by 1 plus A1 times A2 times beta times Vn. That means now, the overall output voltage of this amplifier is equal to VO1 plus VO2. And as you can see, it can be given by this expression. So in this case, the first part represents the amplification of the input signal, while the second part represents the amplification of the noise signal. So here, if we take the ratio of these two parts, then we will get the signal to noise ratio of this amplifier. And in this case, that is equal to Vs divided by Vn times A2. That means now the signal to noise ratio has been improved by the factor of A2. So in this way, using the negative feedback, it is possible to improve the signal to noise ratio and it is possible to reduce the effect of the noise or the interference on the amplifier circuit. Then if we see the next effect, then this negative feedback increases the bandwidth of the amplifier. So let's say we have one amplifier whose midband gain is equal to Am, or in the logarithmic scale that is equal to 20 log Am. So as you can see, this amplifier provides the constant gain in the mid frequencies. And as we go beyond or above these midband frequencies, then the gain starts reducing. So here, this FH is the upper cutoff frequency, while the FL is the lower cutoff frequency. So as you know, the cutoff frequency is the frequency at which the gain of the amplifier reduces by the 3 dB from the maximum value. So here we are assuming that if we are going beyond these cutoff frequencies, then the gain of the amplifier is reducing at the rate of 20 dB per decade. So here the bandwidth of the amplifier is equal to FH minus FL. So we can say that here without the feedback, this FH is the upper cutoff frequency of the amplifier, while the FL is the lower cutoff frequency. and the gain of the amplifier is equal to AM. But with the feedback, this gain will reduce by the factor of 1 plus A beta. Or in the decibel, it will reduce by this 20 log 1 plus A beta. But at the same time, if you see, then the bandwidth of the amplifier will also increase. So now, this upper cutoff frequency is equal to FH dash, while the lower cutoff frequency is equal to FL dash. So here, this upper cutoff frequency FH dash will increase by the factor of 1 plus A beta. And likewise, this lower cutoff frequency will also reduce by the same factor. That means now, due to the negative feedback, the overall bandwidth of the amplifier will increase. So now mathematically, let us prove that how this negative feedback modifies the upper and the lower cutoff frequency of the amplifier. And first, let us see the effect of this negative feedback on the upper cutoff frequency. So to find the upper cutoff frequency, we will consider this part of the frequency response. And as you can see, it looks like a response of the low pass filter. So this part of the gain response can be given as this AM times this omega h divided by s plus omega h. So here the gain response of the amplifier is represented in the Laplace domain. So here this AM is the midband gain of the amplifier and this omega h is the higher cutoff frequency of the amplifier. But here it is represented as the angular frequency. So we can say that this omega h is equal to 2 pi times fh. So first, let us see how this response represents the response of the low pass filter. So further, the same expression can also be written like this. So basically, both numerator and the denominator is divided by this omega h. And now, let us replace this s by j omega. That means now, this expression can be written as a of omega that is equal to am divided by this j omega divided by omega h plus 1. So in this expression, whenever this omega is much lesser than omega h, then this first term will be lesser than the 1. And in that condition, this a omega is approximately equal to am. But whenever this omega is equal to omega h, then the same expression can be written as am divided by j plus 1. Or if we just consider the magnitude, then that is equal to am divided by root 2. That means at the omega h, the gain will become am divided by root 2. Or in the decibel, it will reduce by the 3 dB. So we can say that this expression represents the response of the low pass filter. Or in this case, it represents this part of the frequency response. So this response is the frequency response of the amplifier without feedback. But now, let us see the response of this amplifier with the negative feedback. So with the negative feedback, the closed loop gain of the amplifier can be given as this a divided by 1 plus a beta. So now, let us put the value of as in the given expression. So if we put the value, then this expression can be written like this. That is equal to am divided by s divided by omega h plus 1 divided by 1 plus this am divided by s divided by omega h plus 1 times beta. So now, if we further rearrange the same expression, then it can be written like this. So here, this s divided by omega h plus 1 will get cancelled out over here. And further, the same expression can be written as am divided by s divided by omega h plus 1 plus am times beta. So now, if we divide both numerator and the denominator by this 1 plus am beta, then further this expression can be written as am divided by 1 plus am beta divided by this 1 plus this s divided by this omega h times 1 plus am beta. Or we can say that is equal to am dash divided by 1 plus this s divided by omega h dash, where this am dash is the new midband gain with the feedback. And as you can see over here, that is equal to am divided by 1 plus a beta. And similarly, if we see this omega h dash, then that is equal to omega h times 1 plus a beta. So as you can see, this new cutoff frequency increases by the factor of 1 plus a beta. So similarly, Now let us see the effect of the negative feedback on the lower cutoff frequency. So for the lower cutoff frequency, we will consider this part of the frequency response. So as you can see, it looks like a high pass filter response. And mathematically, it can be expressed by this expression. That is equal to Am times S divided by S plus omega L, where this omega L is the lower cutoff frequency. And once again, here it is represented as the angular frequency. That means the omega L is equal to 2 pi times Fl. So first of all, let me show you how this expression represents the response of the high pass filter. So further, this expression can be written as Em divided by this omega L divided by S plus 1. So basically, both numerator and the denominator is divided by the S. So here, this expression is represented in the Laplace domain. But now, if we replace this S by the j omega, then further this expression can be written as this Am divided by this omega L divided by j omega plus 1. Or further it can be written as this Am divided by this 1 minus this j omega L divided by omega. Because as you know, this 1 divided by j is equal to minus j. That means further, the same expression can be written like this. So now whenever this omega is much greater than omega L, that means whenever we are at this side of the frequency response, then this term will be much lesser than 1. And in that condition, this A omega is approximately equal to Am. But as the omega approaches the omega L, then the value of the A omega will reduce. And whenever this omega is equal to omega L, then in that condition, the expression can be written as this Am divided by 1 minus j. And if we just consider the magnitude, then that is equal to Am divided by root 2. That means at the lower cutoff frequency, the amplitude of this expression will reduce by the factor of root 2. Or in the decibel, it will reduce by the 3 dB. So we can say that indeed this expression represents the response of the high pass filter. So this is the response of the amplifier without the feedback. But now let us see with the feedback how it gets modified. So once again, without the feedback, this is the gain of the amplifier. And with the feedback, it can be given as this A divided by 1 plus A beta. So in this expression, now let us put the value of the AS. So by putting the value, the same expression can be written like this. That is equal to Em divided by this omega L divided by S plus 1 divided by this 1 plus this Em divided by omega L divided by S plus 1 times beta. So now, if we multiply both numerator and the denominator by this omega L divided by S plus 1, then further this expression can be written as this Am divided by omega L divided by S plus 1 plus this Am times beta. So now, let us divide both numerator and the denominator by the factor of 1 plus A beta. So if we do that, then further this expression can be written as this Am divided by 1 plus A beta divided by this 1 plus this omega L divided by S times 1 plus A beta. Or further it can be written as this Am dash divided by 1 plus omega L dash divided by S, where this Am dash is equal to Am divided by 1 plus A beta. And if you see the omega L dash, then that is equal to omega L divided by 1 plus A beta. So this is the expression of the closed loop gain with the feedback. And as you can see, this new lower cutoff frequency is reducing by the factor of 1 plus A beta. That means due to the negative feedback, the closed loop gain reduces, but at the same time, the bandwidth of the amplifier also increases. So let us take one example, and through some numbers, let us understand it in more detail. So let's say we have one amplifier whose open loop gain is equal to 10 to the power 4. And whenever it is used with the feedback, then this feedback factor is equal to 0.1. Moreover, in the open loop condition, this is the frequency response of the amplifier. So here, the upper cutoff frequency is equal to 50 kHz and the lower cutoff frequency is equal to 100 Hz. So with the feedback, now let us find the closed loop gain of this amplifier, and let us also find out the new lower and the upper cutoff frequency of this amplifier. So with the feedback, if we see the closed loop gain of the amplifier, then it will reduce by the factor of 1 plus A beta. Or in this case, this 1 plus A beta is equal to 1 plus this 10 to the power 4 times 0.1, and that is roughly equal to 1000. So we can say that this closed loop gain is equal to A divided by 1 plus A beta, or in this case that is equal to 10 to the power 4 divided by 1000, that is equal to 10. Similarly with the feedback, if we see the upper and the lower cutoff frequency, then this upper cutoff frequency can be given as this fh times 1 plus A beta. So in this case that is equal to 50 kHz times 1000, or we can say that the new upper cutoff frequency is equal to 50 MHz. While if we see the lower cutoff frequency, then it can be given as FL divided by 1 plus A beta. So now it will be equal to 100 Hz divided by 1000, or that is equal to 0.1 Hz. So as you can see over here, with the feedback, now the closed loop gain has been reduced by the factor of 1000. But if we see the bandwidth, then it will also increase by the same factor. So let us see that. So without the feedback, if you see the FH and the FL, then that is equal to 50 kHz and the 100 Hz. That means without the feedback, the bandwidth of the amplifier is equal to 50 kHz minus 100 Hz, or that is equal to 49.9 kHz. So roughly we can say that that is equal to 50 kHz. And if we see the gain bandwidth product, that is the multiplication of this gain and the bandwidth, then that is equal to 10 to the power 4 times 50 kHz. Or we can say that that is equal to 5 times 10 to the power 8. So this is the gain bandwidth product without the feedback. But now let us see the same thing with the feedback. So with the feedback, we have seen that the closed loop gain is approximately equal to 10. But now the new upper cutoff frequency is equal to 50 MHz, while the lower cutoff frequency is equal to 0.1 Hz. That means now if we see the bandwidth of the amplifier, that is fH dash minus FL dash, then that is equal to 50 MHz minus 0.1 Hz, and that is roughly equal to 50 MHz. So as you can see, although with the feedback, the gain has been reduced by the factor of 1000, but by the same factor, the bandwidth of the amplifier has been increased. And if we see the gain bandwidth product, then it will almost remain same. So in this case, if we see the gain bandwidth product, then that is equal to 10 times 50 MHz, and that is also equal to 5 times 10 to the power 8. So we can say that with the feedback also, the gain bandwidth product of the amplifier will almost remains constant. So in this way, with the negative feedback, the bandwidth of the amplifier will increase. So here is the list of all the properties of the negative feedback. And here, out of the 5 mentioned properties, we have already seen the 4 properties. So now, depending on the feedback topology, the input and the output impedance of the amplifier will get modified. So here, briefly first of all, let us understand what do we mean by the feedback topology. So in this feedback amplifier, when we are sampling the signal, then the sampled signal can be either voltage or the current. And similarly, when we are sending the feedback signal back to the input side, then this feedback signal can be either voltage or the current. So depending on whether we are sampling the voltage or the current, and likewise whether we are sending voltage or current on the input side, we can have total 4 different feedback topologies. So in the next video, we will learn about that in detail. And for each feedback topology, we will also find out the input and the output impedance. But I hope in this video, you understood the effect of the negative feedback on the different properties of the amplifier. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.